Welcome to Unmatchable people. Welcome everybody. How you guys are doing? This meeting is being recorded. Okay. Okay. Is it so? Bella ciao, bella ciao, bella ciao, ciao, ciao. Okay, people. Welcome back. Okay. So just to make sure that all of you are understanding and enjoying probability. I did not share this yet. What the hell is happening? Now it is shared. Here we go. Here we go. Okay. No, 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 no. Bring the eraser to me. I don't want to use your tools, dear PPT. So we are currently at the last phase of learning probability 2.0. And in probability 2.0, we understood multiplication law. Multiplication law of probabilities. Multiplication law of probability. And then we are solving some problems based on combined application. Problems based on combined application of addition law of probability and multiplication law of probability. Problems based on combined application of addition law and combined application of multiplication law. So tell me, how many problems are we done with? I take you to the next one. Tell me.
15, sir.
15.
Yes, sir.
As a 15th problem, let's say a salesman. Now, if it is a salesman, he will be naturally selling a product. Salesman is selling a product. And probability of a customer, of a person, probability from the past data, it is seen that probability of a person agreeing to buy the product, probability of a person agreeing to buy the product from the past data, the probability of buying the product is only 0.2. Only 2 out of 10 persons on an average agree to buy the product. So a salesman is selling a product on some marketplace. You know, this salesman is not having any shop or something. This is just, the salesman is just asking people that buy this pen, buy this pen, buy this pen. And probability of a person agreeing to buy the product is only 20%. Then what is the probability then I need to calculate what is the probability that a product will be sold. What is the probability that a product will be sold by asking max to 3 persons? What is the probability that a product will be sold by asking maximum to 3 persons? So this salesman in a busy marketplace on a street is carrying some pens and offering those pens to everybody that would you buy this? Would you buy this? And the probability of any one person buying the pen is 0.2 only, 20% only. Then what is the probability that a product will be sold by asking maximum to 3 persons? Maximum 3 persons. What is the probability that he will get a success in maximum 3 attempts? So such problems which are based on combined application of, such problems are always based on combined application of addition law and multiplication law of probability. This is combined application of addition law and multiplication law. This is combined application of addition law and multiplication law. Okay. So you always need to break such problems into a combination of and or. Always try to break your problem into a combination of ands, ors. If you can break your problem successfully into ands and ors, then your problem will be done easily. So let us try to break our problem into this kind of arrangement, that a product will be sold maximum by a product will be sold, and let's remove a. Let's say he's having only a single unit left. So there is only a single unit of product left. Let's make it a little uncluttered problem. Let's say there is only a single unit of product left. So that the product will be sold by asking max to 3 people, by asking max to 3 persons. Can you break it into ands and ors? Yes. How? That first person buys the product. He gets the success just now. He asks one person, Mr. Changu, would you take, this is the only unit remaining, I'm giving it at a discount. Would you take it? Changu agrees. Changu agrees, product is sold, program terminated. Changu agrees to buy the product and product sold. And since there is only a single unit, the program is terminated. But there is one more possibility. So if there is one more mutually exclusive possibility, we place an or. First person, I ask the first person and first person agrees to buy my product, the job is done. Or the first person is going to refuse to buy. And then I try. And then I try for the second person, and the second person agrees to buy the product. And the second person says, yes, I was waiting for this pen. This pen is very magical pen. I'm going to do some magics with this pen. So come on, I will take this pen. Now you notice that we have an and coming into the picture. But there is one more possibility. If you are looking for maximum 3 persons, If you're looking for maximum 3 persons, then there is one more possibility that first person is going to not agreeing to buy the product, and second person also not agreeing to buy the product, and third person finally agreeing to buy the product. First person buying the product, or there is one more possibility that first person refuses and the second person buys the product, or there is one more possibility that first person refuses, second person also refuses, and third person buys the product. So we notice that we have a combined application of multiplication law, multiplication law, multiplication law, and then there is addition law, addition law. Then there is addition law, addition law. So each probability separated by or will be added. Each probability separated by an or will be added. And then we have this representing one event, this representing one compound event, and this representing another compound event. 3 compound events are mutually exclusive. And these 3 mutually exclusive compound events can satisfy my overall event, my global event, my resultant event. So now I know that how to proceed, that probability that first customer itself is going to buy, or first customer is going not to buy, and second customer decides to buy, or first one is going to refuse and second one is going to refuse again, and second one is going to refuse again, and third one is going to agree that yes, this is the pen I was waiting from last 20 years. Mr. Changu, thanks for selling it. So first person will buy the pen, that probability is 0.2. And here we are, let's not write the values yet. Probability that first person will buy, and here probability that first person will not buy into probability that the second person will buy. Now, why are we using multiplication law? Why are we using multiplication law? Because there are compound sample spaces. Because there are repeated random experiments. Asking to one person that would you buy my product has yes or no, a sample space of 2 possible outcomes. Asking to second person is another sample space having once again yes and no. Asking to third person is a third random experiment, again having a sample space of yes or no. Yes probability is 0.2 and no probability is 0.8. So asking one person is one random experiment, asking second person is another random experiment. Overall, it becomes compound random experiment. Overall, it becomes compound random experiment. Plus the first person refuses to buy the product, and the second person also refuses to buy the product, and wait a moment. And finally, the third person agrees to buy the product. Telling this once again to you that asking to one person is one random experiment, asking to second is another random experiment, asking to third is a third random experiment. Since there are multiple random experiments, it becomes a compound random experiment. And wherever there is a compound random experiment, there only you use multiplication law of probabilities. There only you use multiplication law of probabilities. So first person agrees to buy the product, 0.2. First person refuses to buy the product, but second person agrees to buy the product. First person refuses to buy the product, and second person also refuses to buy the product, and the third person is going to buy the product. What is the final answer? What is the final answer? 0.8, 0.2 plus 0.8 into 0.2 plus 0.8 into 0.8 into 0.2. This is 0.488. There are 48% chances that by asking to maximum 3 persons, the product will be sold. There are 48.8% chances. Even though asking to one person seems to be such a disappointing scenario, only 20% chances are that he will say yes. Only 20% chances are that the person is going to say, yes, I would buy your product. Only 20% chances. But if you keep asking back to back 3 people, then there are chances that 50% chances that by asking to 3 people, you will be able to sell the product. Cool. So now we know. Now we have solved one more problem based on combined application of addition law and multiplication law. We know how to do the things now. Only by solving multiple problems, you will get a command over this topic called probability. Let's solve one more problem based on combined application of addition law and multiplication law. Let's solve one more problem. Delete. This time, let us solve an interesting one. Let's say we are going to play a game. If die turns to I win, we are going to play a game of rolling the die, and if die turns to I win, and if the die turns 5, you win. The die turns 5, you win. Okay. So we are going to play a game and we are going to roll the die. And if the die turns 2, I win. And if the die turns 5, you win. Okay. Here are rules of the game. Here are rules of the game. Rule of the game number 1, that since you are my student, you get first chance. To roll. Okay. And second rule, that the game is terminated as soon as someone wins. Game terminates as soon as someone wins. Okay. What is the probability of me winning? What is the probability of me winning the game? So turn by turn, we both do this. You roll the die, and if 5 comes, you win. Then I roll the die. If 2 comes, then I win. And it's not like you roll the die and 2 comes, then I win. No, that's not the case. You roll the die, and even if 2 comes, I do not win. Okay, let me make it very clear here. You roll the die, and then 5 comes, then you win. If I roll the die and 5 comes, then you don't win. You only roll and then 5 comes, then you win. Otherwise, this statement will have no meaning. If you win by coming 5, even I roll, then there is no meaning of you getting the first chance, because you can win even if I get the first chance. So you roll and then 5 comes, then you win. And I roll the dice, then 2 appears, and then only I win. Since you are my student, I grant the first chance to you, number 1. And rule number 2, the game terminates as soon as any one person is going to win. Okay? What is the probability of me winning the game? What is the probability of me winning the game? You will have to learn to always break your given event. Always break your given event into a combination of and ors. You will have to learn breaking the given event into a combination of ands and ors. जब तक आप किसी भी गिवन इवेंट को एंड्स और ऑर्स में ब्रेक करने की कैपेबिलिटी नहीं बिल्ड करते हो, आप प्रोबेबिलिटी के मास्टर नहीं हो सकते. You can become a master at probability only by building the ability to break any event into the combination of ands and the combination of ors. So let's try to break this event. You see, you get the first chance. So maybe you are going to win in the very first chance, and I don't get any chance to win ever. I don't get any chance to win the game ever. Maybe the very first chance, you roll the dice, 5 comes, you win, game is terminated, over. I only see that I did not even get first chance. I did not get even the very first chance to play the game. Forget about winning the game. So I have the chance of winning only when I get a chance of playing. And when I get a chance of playing, tell me, when I get a chance of playing, you get the first chance, and I'm interested in what is the probability of me winning. Then tell me, I win only if I get a chance to play. And I will get a chance to play only if you lose in the first chance. Only if you lose in the first chance, then I get the chance to play and I win. The game is terminated. I won. Over. The game is terminated. I won. The game is over. Khatam. Tata, bye bye. Okay, tata, bye bye. Khatam. The game is terminated. I won the game. Let's go home. Let's go home. Okay. But there is one more way that I can win. You take the first turn. and unfortunately you lose. And then obviously I'm going to take the next turn, but I also lose. And then I wait for you to lose. Otherwise, if you win, I will never get another chance again. If you win, I will never get another chance again. So I wait you to lose again. And then I get the next chance, and finally I win. Over, game is terminated now. So this is one compound experiment in which way I can win. This is another compound experiment in which way I can win. There is one compound experiment, you lose and I win, and then there is another compound experiment, you lose and I lose, and then you again lose and I then win. Or might be you lose and then I also lose. You always get the first chance. That's clear, na? You get the first chance to play. So you get the first chance to play and you lose, then only I get a chance to play. Otherwise, I will not even get a chance to play. Otherwise, I will not even get a chance to play. So you play and you lose, then I get a chance to play and I also lose. And then you get a chance to play and then you lose again. And then I get a chance to play and I lose again. Then I wait for you to lose once again. Then I wait for you to lose once again. And then, my dear friends, finally, it's my luck. Finally, it's my luck. And I win. This is another compound experiment. This is another compound experiment in which I have a chance to win. But mind it, mind it, mind it, mind it. This compound experiment is one way for me to win. This compound experiment is another mutually exclusive way for me to win. This compound experiment is yet another mutually exclusive way for me to win. So all of them, because they are mutually exclusive, either first one will happen and game will terminate, or second one will happen and game will terminate, or third one will happen and game will terminate, or fourth one will happen and game will terminate, or fifth one will happen and game will terminate, or sixth one will happen and game will terminate. It will keep on going until one person wins and the game is terminated. Until one person is going to win and the game is terminated. All right. All we need to do now is to calculate these probabilities. By the way, it will keep going on. So let us calculate these probabilities now. Let's calculate these probabilities. Probability of you losing is 5 by 6. Because now you understand. Everybody is having, in any given chance, everybody is having 1 upon 6 chances of winning and 5 upon 6 chances of losing. Only one favorable event is there of anybody winning. So 1 upon 6 chances of winning and 5 upon 6 chances of losing. If a 2 comes, then again, I also have in any given term, in any given chance, I have 1 upon 6 probability of losing and 5 upon 6 probability of winning. So I'm going to write you lose and then I win and the game gets terminated. This is one way. Or you lose the game, you lose your chance, then I lose my chance, then you lose your chance again, then finally I win. Or you lose the chance and you lose the chance and I also lose the chance and you lose the chance again and I lose the chance again and once again you lose the chance Once again, you lose the chance, you lose your chance. And finally, this time I got lucky. This time I got lucky. This will keep going on. Now you will have to apply multiplication law. Now we 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 will have to apply multiplication law. So let us now apply multiplication law. You losing the game has how many chances? You losing the game has 5/6 chances, and means multiplication law. And then I win the game. This is first. And then you lose the game, and I lose the game. I lose the game, and then you lose the game again, and then I win the game. And here you lose the game, and I lose the game. I lose the game. I lose the chance, actually, not game. And you lose your chance. I lose my chance. You lose, I lose, you lose, I lose. And then you lose your chance again. And then I win my chance. Like this, the game can continue forever. There is a chance that the game can continue forever. It might go up to infinity. The game can actually go up to infinity. You never know. It's a total randomness. It will be terminated as soon as someone is going to win. And either you are going to win in this possible way, or you are going to win in this possible way, or I'm going to win in this possible way. Or if these three doesn't happen, then there is one more way waiting. Dash, 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 wala way. There is dash, dash, dash way waiting. So now I can take 5/36 common. And if I take 5/36 common, I have 1 plus 5/36 is common. So another 5/36 is remaining. And here 5/36. Oh, no, 5/36 is common. So 25/36 is remaining. In the second term, 25/36 is remaining. 25/36 is remaining. In third term, 5/36 is common. So 25/36 square is remaining. 25/36 square is remaining. Naturally, I have not written further possibilities, but if I would have written further possibilities, I must have got 25/36 cube remaining, 25/36 power 4 remaining, 25/36 power 6 remaining, 25/36 power 7 remaining, 25/36 power 8 remaining, and so on and so forth. Whatever is remaining inside the braces represents an infinite geometric progression. Whatever is remaining inside the braces represents an infinite geometric progression. If you know how to solve infinite geometric progression, that's great. And if you don't know it from today, that if there is A and there is AR and there is AR square and there is AR cube and there is AR power 4 and there is AR power 5, then, and it goes up to infinity, then my dear friends, I get A upon 1 minus R as the sum of such a geometric progression. This is a geometric This is a geometric progression. And geometric progression, infinite geometric progression sum becomes A upon 1 minus R. So 5/36 is common anyways. 5/36 is common anyways, and we have A value 1 and R value 25/36. So 1 upon 1 minus 25/36. I get 5 upon 36 and I get 36 upon 11. I get 36 upon 11. 36 and 36 get cancelled. I have less than 50% chances of winning the game. Why not equal? Why your chance of winning the game and my chance of winning the game is not equal? Why I have less than 50% chances? I have only 45.45% chances. Why? Why your chance of winning the game is higher and why my chance of winning the game is less than 50%? Tell me. Intuition
First,
behind it.
first chance is mine, sir.
Exactly. First chance is yours. Final overall result is intuitive because you get the first chance to play the game. That's why you have more than 50% chances of winning the game, and I don't get the first chance to play the game. Therefore, I have less than 50% chances of winning the game. I have less than 50% chances of winning the game because I don't play the first chance. Cool. So enough of these type of problems where we have combined application of addition law and multiplication law. We move ahead to the next type of problems in probability. Actually, next type of problems are not going to be different. They are going to be similar problems, but they will need some more weapons in our pocket. So far, so good. Let us very quickly give a recap of everything that we have done in probability. Probability started with three axioms. Probability started with three axioms. Axiom number one is that any event can never have negative chances of occurring. Worst case, it will have zero chance of occurring. And probability of whole sample space is going to be 1. Probability of whole sample space is going to be 1. And probability of A union B. Probability of A union B is probability of A union, probability of A plus probability of B. These were three simple axioms. Then, using these three axioms, we covered a single finite sample space. A single finite sample space. A single finite sample space with capital N number of equally likely outcomes. Capital N number of equally likely outcomes. In that case, each outcome, whether it is outcome element number 1, or it is element number 2, or it is element number 3, all of them will have the probability 1 upon n, 1 upon n, 1 upon n, 1 upon n, and then there is an event that is satisfied by E1, E5, like that. Let's say it is satisfied by a small n number of outcomes. Then I can write E1 and I can write E5 and I can write En and I can write En, and that becomes 1 upon capital N, and that becomes 1 upon capital N, and that becomes 1 upon capital N. 1 upon capital N, 1 upon capital N, 1 upon capital N. If I'm adding a small n number of times, I get a small n upon capital N. This is how the formula of favorable outcomes upon total outcomes arrives. Then we studied about addition law of probability. In the single sample space, if you define interfering events, in a single sample space only, you define interfering events. Then you use addition law of probabilities, that I'm interested in A. A and B both are defined on same sample space, okay? As of now. As of now, A and B both are defined on the same sample space. So you write it as PA plus PB minus PA intersection minus PA intersection B. Same thing can be written for three events also. A union B union C is equal to probability of A plus probability of B plus probability of B plus probability of C plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A plus probability of A intersection B intersection C. If you remember, we solved rain and star problem. We solved party, green shirt, black shirt, red shirt, green shoes problem. We solved some fluid favorite, thermodynamics favorite problem. We solved. Hello, sir. Hello. What is the exact meaning of probability? Exact meaning of probability is chance of occurrence. Just like my chance of reading your comment was 100%, and therefore I read your comment. Okay. Now this student is like, reply me or I will dislike the video. No. Listen, you even though don't dislike my video, I'm freely giving this service without charging anything to anybody. I'm freely giving this service to people who cannot afford the education on YouTube. But let me clarify that I'm much above, I'm much beyond the levels of getting affected by likes and dislikes. I'm much beyond the phase of getting affected by likes and dislikes and views and all these things. So that just doesn't affect. Doesn't affect means doesn't affect. Okay? Praises, criticisms, likes, dislikes, they are part and parcel of the journey. I'm enjoying the journey rather. So addition law of probability, and then we entered into compound random experiments. And then we entered into compound random experiments. Compound random experiments are interesting, that you have one random experiment defined. You have one random experiment defined with one sample space. You have another random experiment. You have another random experiment defined with another sample space. You have one random experiment defined with one sample space. You have another random experiment defined with another sample space. With another sample space. Okay. And then you have yet another random experiment defined with yet another sample space. So there could be many random experiments, and each random experiment has its own sample space, its own sample space, its own sample space. Random experiment E1 has the sample space S1. Random experiment E2 has the sample space S2. Random experiment EK has the sample space SK. And S1 is having N1 number of elements, S2 is having N2 number of elements, and SK is having total number of possible outcomes NK. Then my dear friends, this overall setup is known as compound random experiment. This overall setup is known as compound random experiment. There is one random experiment having sample space S1 of n1 number of equally likely outcomes. There is another random experiment having sample space S2 with n2 number of equally likely outcomes. There is yet another random experiment having SK sample space having NK number of equally likely outcomes. Then, my dear friends, the compound random experiment defined by encompassing all these random experiments, that compound random experiment will have the sample space S having n number of total outcomes, where n becomes n1 multiplied by n2 multiplied by n3 multiplied by nk, n1 multiplied by n2 multiplied by n3 multiplied by nk. Resultant random experiment is called compound random experiment. Resultant random experiment has this resultant sample space with capital N number of equally likely outcomes, which is N1 into N2 into N3 into N4 into N5 into N6, like that. Now, suppose we define one event in sample space S1, we define one event in sample space S2, we define one event in sample space SK, we define one event in sample space S1, we define one event in sample space S2, we define one event in sample space SK. And this way, we are actually defining one big event in overall compound experiment. In overall compound experiment, we are defining a big event A, which occurs by co-occurrence of A1, A2, A3, A4, A5. So I'm defining one big event, capital A, which occurs by occurrence of A1 in sample space S1, by occurrence of A2 in sample space S2, by occurrence of A3 in sample space S3, by occurrence of AK in sample space SK. Then what will be the probability of this global event? Probability of this global event will very interestingly will be simply the product of probabilities of A1, A2, A3 up to probability of AK. The key word is that A gets satisfied by satisfying A1 and A2 and A3 and A4 and A5. The keyword is that A gets satisfied by satisfying A1 and A2 and A3 and A4. So this global event A gets satisfied by co-occurrence of A1 and A2 and A3 and A4 and A5, and is the keyword to use multiplication law of probabilities. To use the multiplication law of probabilities, the keyword is and. When local events are connected with and, then you use multiplication law of probabilities. Entire probability thing that we have done so far, I have summarized on a single page. Take a screenshot and enjoy. Everything that we have done in probability so far. We have summarized it. Now we are going to move ahead to the next task of probability. And what is going to be the next task of probability? That starts. Of course, we have solved problems based on combined application of. Then we have solved problems based on combined use of addition law and multiplication law. Combined use of addition and multiplication law. Now taking you to the next thing. And that starts probability 3.0. This much we covered. I don't know about you, but I'm enjoying. I have always enjoyed this topic. These are the topics we covered in probability 1.0, and these are the topics we covered in probability 2.0. Starts the next sequel of this beautiful topic. Probability 3.0. It seems nothing more can be formulated, no? Once you solve problems based on combined use of addition law and multiplication law, you start developing a feeling that this is probably the charam, this is probably the limit of this topic. What else can be formulated? I mean, you think about that salesman problem, you think about that dice game problem between me and you, you think about that Changu getting convicted by court, that problem, you think about that Changu and Mangu writing exam together, that problem, and you think and you notice that there is nothing more. But we cannot start probability 3.0. We have one more thing to cover. And that's actually based on this combined use of law of addition and law of multiplication only. This combined use of addition law and multiplication law can sometimes get murky. It can sometimes become too complicated. Problems based on combined use of addition and multiplication law, sometimes they can become too complicated. Too complicated means too complicated. Let me take an example to help you understand. We are still, I'm sorry, 3.0 can't be started yet because we have task to cover one more important thing. So we are still at this combined use of addition law and multiplication law of probability. And sometimes this might become frustratingly lengthy to use multiplication law and addition law in the way we have learned them. You tell me, what's the score?
17, sir.
17th now. So as a 17th problem, let's say As a 17th problem, let's say I'm tossing a coin. I'm tossing a coin and I'm tossing the coin 4 times. Okay. Calculate the probability of getting 1 head. Like exactly 1 head. I'm not saying at least 1 head. I'm not saying at max 1 head. No. Calculate the probability of getting 1 head. Okay. So tossing a coin 4 times actually gives you 4 sample spaces. Sample space number 1, you have head and tail. Sample space number 2, you have head and tail. Sample space number 3, you have head and tail. Sample space number 4, you have head and tail. Again, it becomes the problem of compound random experiment. It becomes the problem of compound random experiment. It is essentially the problem of compound random experiments. So I am pretty sure that multiplication law will come into the picture. Since it seems to be a problem based on compound experiment, one thing is very clear, multiplication law will be used. Getting 1 head can be satisfied. Out of 4 tosses, getting 1 and exactly 1 head, not at least 1 head. We are interested in exactly 1 head. Getting exactly 1 head can be satisfied in multiple or combinations, that you get head and then you get tail. Or there is one more way. You get tail and then you get head and then you get tail and tail. Or there is one more way, that you get tail, you get head, and you get tail. Or there is one more way, that you get tail, you get tail, and finally you get head. And finally you get head. These are 4 possible tariqas in which you can get a head. So actually it is a multiplication law combined with law of addition. It is a multiplication law. Multiplication law is this blue one. 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 But those multiplication laws are combined with addition law of probability, because there are mutually exclusive ways of satisfying your events. Why blue part is multiplication law? Because you get head and you get tail and you get tail and you get tail. You get tail and you get head and you get tail and you get tail. You get tail and you get tail and you get head and you get tail. You get tail and you get tail and you get tail and you get head. When you say and multiplication law is, when you say and multiplication law is asking to be used. When you say or addition law is to be used. So I can now write H and T and T and T plus probability of T and H and T and T, or probability of T and T and H and T, or probability of T and T and H. Just like we solved Changu Mangu passing the exam problem. Just like we solved Changu getting convicted by court problem. Just like we solved me and you playing the game of dice problem. All these were combined use of addition and combined use of addition law and combined use of multiplication law. This is 1 by 2 into 1 by 2 into 1 by 2 into 1 by 2. This is 1 by 2 into 1 by 2 into 1 by 2 into 1 by 2. This is 1 by 2 into 1 by 2 into 1 by 2 into 1 by 2. This is 1 by 2 into 1 by 2 into 1 by 2 into 1 by 2. You realize that if somebody would have told you getting one head out of 4 tosses is getting one head and 3 tails, it's only now differing by placement. It's only now differing by placement. You are always doing 3 tails, 1 head. So this value and this value and this value and this value has to be equal, because you in all these or possibilities, this is actually same thing as this, same thing as this. Numerical value of first blue probability and numerical value of second blue probability and numerical value of third blue probability and numerical value of fourth blue probability are certainly going to be equal, because every time you are multiplying 3 t's with one head. You're multiplying 3 t's with one head. You're multiplying 3 t's with one h. 3 t's with one h. So if somebody told you right away that there are 4 ways to place, there are out of 4 times tosses, there are 4 ways to place a head. You can place head at first place, you can place head at second place, you can place head at third spot, you can place head at fourth spot. Then you don't need to do all this. You don't need to do all this, adding and adding and adding and adding again. You don't need to do all this adding and adding and adding again and again and again. You could have calculated just one value. And if somebody told you that there are 4 tariqas to fill the spots by your desirable event, then you would have simply written this 1 by 2 power 4 value once, 1 by 2 power 4 value once, and then you'd have multiplied with that number of ways in which head can be placed at a spot. Head can be placed in 4 spots. We need to find out a way, a scientific way, not trial and counting way, not manually counting. This is manual counting. That put H at first spot, put H at second spot, put H at third spot, put H at fourth spot. This is manual counting. If somehow somebody would have told me, that, look, all probabilities separated by plus signs, are equal, man. They are equal. Look, 1 by 2 power 4, 1 by 2 power 4, 1 by 2 power 4, 1 by 2 power 4. All of them are equal, equal, equal. So if somebody would have told me that how many number of ways are there to place one H to place one H in 4 spots, I would have multiplied and I would have got the result directly instead of doing this manual counting. Instead of doing this manual counting. Hello, Tower Infinity. So instead of doing this manual counting, I must have got the results. Let's develop a.
Sir, I have one doubt, sir.
Yes, tell me.
Actually, we are tossing a coin. After first, when we toss a coin, head will come, sir. Again, why we are tossing, sir? We have to go to second chance, no, sir.
No. The question is not saying it's kind of termination or something.
Okay.
Question is not saying that getting one head is our target, and when target is achieved, then we don't toss. Question says that we tossed 4 times. Question doesn't say the target first. Question says we tossed 4 times. We will toss 4 times. Out of 4 times, we want to get one head. It's not like that dice wala game that once you get the head, the game is over. No, that's not the case. We are not tossing till we get success. We are tossing by fixed numbers. We have fixed number of tosses assigned. If question said, we keep tossing unless we get ahead, then that was a problem like salesperson. If question says we keep tossing unless we get head, terminate. Or we get tail, toss again, get head, terminate. Or we get a tail, toss again, get tail again, toss again, get a head, terminated. Or get a tail, and get a tail, 4th chance, get a head, terminated. Or now this problem will become similar to which problem? This problem will become similar to which problem? If I have to toss, can I ask a doubt? Yes, of course, you can ask. Tower Infinity. So this kind of problem that I toss, and unless I get ahead, I keep tossing. This problem is that salesperson problem. I asked the first person. He refused. He bought the product. Product is gone. Over. I asked the first person and he did not buy the product. Then I asked the second person and he agreed to buy the product. Or first person refused to buy the product. Second person refused to buy the product. And then third person finally agrees to buy the product. First person refuses to buy the product. Second person also refuses to buy the product. Third person also refuses. Fourth person agrees. The product is gone. The product is gone. The sale is done. The story is over. This is a different problem. Let's find a scientific way. to determine this. Let's find a. I have a doubt in this question, but sir, how to ask you via audio? Oh, and now on YouTube, unfortunately, no audio is allowed, and obviously, this is a paid course running, so on Unmatchable, only those learners can join. Try writing it. Try writing it. I will answer. I wish YouTube also brings with some kind of audio response. So let's find a scientific way to determine this. Number of ways to place one H in 4 spots. There are 4 spots, and all I need is fill one spot with H. Let's find a scientific way to determine these kind of things. Let's do this. Let's say we have 5 characters. Or, yes, okay, 5 characters. Now, using these 5 characters, how many different arrangements you can make? Or let's keep only 4 characters. So using these 4 characters, how many different arrangements can you make? You can begin with A, second place B. You can begin with A, second place D, C. You can begin with A and second place D. Then the third place is going to have C. And if you are beginning with A and second place is B, if you are, dhyan se samajhiyo, if you are beginning with A and second place is B, then third place has 2 possibilities, C and D. Obviously, fourth place then has only 1 possibility. You begin with A and second place C, then third place has Bhopal and Delhi. And once Ahmedabad, Chennai, Bhopal is filled, then only Delhi is left. Once Ahmedabad, Chennai, Delhi is filled, then only Bhopal is left. Ahmedabad, Delhi, and then Bhopal and Chennai can come to third place. Ahmedabad, Delhi, Bhopal, then Chennai, Ahmedabad, Delhi, Chennai, then Bhopal. So just by keeping Ahmedabad at the first place, just by keeping Ahmedabad at the first place, I have 3 tariqas. I have 3 tariqas to fill the second spot. And with Bhopal, I have further 2 tariqas. With Chennai also, I have further 2 tariqas. With Delhi also, I have further 2 tariqas. So total become 6 tariqas. Of course, after that, only one way is left, one way is left, one way is left, one way is left. So there are, by keeping Ahmedabad at the first place, I have 3 into 2 into 1 ways to arrange. By keeping Ahmedabad at the first place, I have 3 into 2 into 1 ways to arrange the characters. By keeping Ahmedabad at the first place, I have 3 into 2 into 1. Similarly, by keeping Bhopal at the first place, 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 I again have 6 tariqas. Why? Because at the second place, I have 3 choices, either Ahmedabad or Chennai or Delhi. And with Ahmedabad at the second place, I have 2 tariqas, either Chennai or Delhi. With Chennai at the second place, I have 2 tariqas, Ahmedabad and Delhi. With Delhi at the second place, I have 2 tariqas, Ahmedabad and Chennai. So there are, with Bhopal fixed at the first place, I have 3 choices at the second place, and then with each of these choices, I have 2 choices, 2 choices, 2 choices. So 3 into 2. Further, I have only 1 choice remaining. Further, I have only 1 choice remaining. Further, I have only 1 choice remaining. So only 1 choice is remaining. Similarly with similarly with Chennai at the first place. This we have done with Ahmedabad at the first place and then Bhopal at the first place. Now let us do it. Now let us do it with Chennai at the first place. Chennai at the first place, Chennai at the first place, Chennai at the first place, Chennai at the first place. Second place can be Ahmedabad, second place can be Bhopal, second place can be Delhi. Second place can be Delhi. With Ahmedabad at the second place, we have either Bhopal or Delhi. With Bhopal at the second place, we are left with either Ahmedabad or Delhi. With Delhi at the second place, I'm left with either Ahmedabad or Bhopal. So with Chennai at the first place, we have 3 choices for the second place. And with each of the 3 choices, we again have 2 choices. After that, only 1 choice. After that, only 1 choice is left. 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 Last. Delhi at the first place, Delhi at the first place, Delhi at the first place, Delhi at the first place. With Delhi at the first place, you can have Ahmedabad at the second place, you can have Bhopal at the second place, you can have Chennai at the second place. You can have Ahmedabad at the second place, you can have Bhopal at the second place, you can have Chennai at the second place. With Ahmedabad at the second place, you have 2 choices further, Bhopal and Chennai. With keep in mind, Delhi is already taken. With Bhopal at the second place, I have 2 choices, Ahmedabad and Chennai. With Chennai at the second place, I have 2 choices, Ahmedabad and Bhopal. Last choice, only one thing is left. 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 So once again, with Delhi at the first place, I have 3 choices. With each of the 3 choices, I have 2 choices further. Last place, I have 1 choice. Naturally, I have 3 into 2 into 1, repeating 4 times. I have 3 into 2 into 1, repeating 4 times. I have 3 into 2 into 1, repeating 4 times altogether. So how many total possible arrangements are using 4 objects at 4 places? How many total arrangements do we have? Using 4 objects at 4 places, I have total possible arrangements 4 into 3 into 2 into 1. You can see the pattern and conclude that if you would have tried 6 objects at 6 places, you would have got 6 into 5 into 4 into 3 into 2 into 1. Number of arrangements of four objects at four places, you get 4 into 3 into 2 into 1. In general, number of arrangements of n objects at n places. In general, number of arrangements of n objects at n places would be n into n minus 1 into n minus 2 up to 3 into 2 into 1. Because this whole multiplication occurs, so many phenomenon, so many problems. Because this multiplication occurs in so many phenomena, in so many problems, in so many physical applications, in so many instances, people gave it a shorthand notation. People said that who would write this 10 into 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1 again and 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 again. Who would write this again and again? I'm not going to write this again and again and again and again and again. So people gave it a shorthand notation, and that shorthand notation is "and surprise." They gave exclamation mark because of this only. That n, if I start from 100, then 100 into 99 into 98 into 97 into 96 into 95 into 94 into 93 into 92 into 90. Oh, bap re, this is such a surprising. So that's why exclamation mark. They got shocked. That's why exclamation mark. We read it as factorial n. We read it as factorial n. n number of objects. If you are placing at n places, if you are arranging at n places, then n factorial ways, n factorial tariqas are there to do this. There are n factorial ways to fill n places with n objects. Conclude it. There are n factorial ways to fill n places with n objects. But suppose now I have n objects, but places are. Suppose now I have n objects, but places are lesser. For example, let's say I have A, B, C, D, but I want to make an arrangement of only 3 characters. Or I have A, B, C, D, but I want to make an arrangement of only 2 characters. I hope you understood this n factorial thing. I hope you understood this n factorial thing. So if you understood this n factorial thing, then we move on to the next problem. The next problem is, so far we have seen number of arrangements of n objects at n places. Now we will see number of arrangements of n objects at r places. This was arranging n objects at n places. Now we are going to arrange as our next task. We are going to arrange n objects at r places. For example, let's find out arrangement of two characters out of these four characters. So I can take AB, I can take AC, I can take AD, I can take BA, I can take BC, I can take BD, I can take CA, I can take CB, I can take CD, I can take DA, I can take DB, I can take DC. Notice that at first place we still have, just like previous arrangement, at first place we still have four tariqas. At second place, my dear friends, at second place we still have, with each of these I have three tariqas. 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 With each of these I have three ways. 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 So I get number of arrangements. How many? I get number of arrangements. How many? Number of arrangements. I get 4 into 3. I get 4 into 3. People said that 4 into 3 into 2 into 1 was such a beautiful thing, no? That 4 into 3 into 2 into 1, that was such a beautiful thing. That was a lovely thing. Unfortunately, this time we are not getting that format. Unfortunately, this time we are not getting that format. If we are not getting that format, we will forcefully introduce that format. If we are not getting that format, we will forcefully introduce that format. Forcefully. I liked that foreshocking and exclamation mark so much that I'm saying that I'm liking it and I want to bring it. I want to bring it into the picture, man. So I forcefully introduce 2 into 1 in the numerator and 2 into 1 in the denominator. I get 4 factorial in numerator. I get 2 factorial in denominator. Can you now generalize? Putting 4 characters at 2 spots. Out of 4 characters, you need to fill only 2 spots. You need to fill only 2 spots. How many ways are there to do this? In how many ways can you do this? You can do this in 12 possible ways. That is 4 into 3. First place, you have 3 tariqas. Second place, with each tariqa, you have 1, 2, 3. With each tariqa, you have 1, 2, 3. With each possibility at first place, you have 3 possibilities at second place. With each possibility at first place, you have 3 possibilities at second place. So 4 into 3. But that format of 5 into 4 into 3 into 2 into 1, which we call 5 surprise, or that format of 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1, which we call 9 shock, 9 exclamation mark, which we call as 9 exclamation mark. I wanted that format, so I have written it like this. Can you generalize it? Arrangement of n objects, arrangements of n objects at r places will be equal to n factorial upon r factorial. My dear friends, in the language of mathematics, this is called permutations of n objects at r places. In the language of mathematics, this is called permutations of n objects at r places. We call it the permutations of n objects at r places. Okay. So are we done with getting our desired thing? Unfortunately, no. Unfortunately, we have still not got what we desired. We are just one more step away. Let's complete it. Next problem. We are done with arranging n objects at n places, arranging n objects at r places, arranging n objects at n places done, arranging n objects at r places done. Now we are going to select r things out of n things. This is the last problem of counting. This is the last problem of counting. So let me just recap. So far, so good. I have so far, so good. N objects arrangement of n objects. First place you can fill with n choices. Second place n minus 1 choices. Third place n minus 2 choices. At last, you are left with only one choice. This is denoted as n factorial. Arrangement of n objects at r places. First place n choices, second place n minus 1 choices. And naturally, as soon as you reach out of n, you reach n minus r plus 1, na? That's it. Because there are only r places. So at first place, you can, let's say 5 objects are there and I want to put them at 2 places. Then I can put 5 and 4. That's it. Over. So 5 minus 1 is the last entry. And 1 can be written as r minus 1. Yes, perfect. Now we have our places filled because naturally simple counting says that 1 to r minus 1 becomes r minus 1 places and 1 additional. So total r places. But people said that let's better introduce all other remaining things in numerator and all other remaining things in denominator. Let's better introduce. Here also we have a series like this, and then some remaining numbers are there. Here I have only this much series. Those remaining numbers are missing. So I'm going to put those remaining numbers by my side. Put those remaining numbers from my side. And what are those remaining numbers? N minus r remaining numbers, na? N minus r remaining numbers, because r numbers you have already filled. Those n minus r remaining numbers are there, so this is the way we get n factorial in numerator and n minus r factorial in denominator. This is called as NPR. Earlier I wrote n factorial upon r factorial because even n minus r was equal. 4 minus 2 was equal to 2. That's why that confusion was there. But actually it should be n minus r in the denominator. Now the last problem. Selecting r objects out of n objects. Go back to your problem. A, B, C, D. And let's say I want to select one of them. Or I want to select two of them. Or I want to select three of them. I want to select all four of them. My dear friends, arrangements unfortunately represent repeated selections. So arrangements can't count as selections. ध्यान से समझियो. Arrangements unfortunately represent repeated selections. For example, arranging these four things with four things, you will have AB, AB, AC, AC, AD, 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 third place C, third place D, third place B, third place C, third place B, third place C, fourth place remaining, 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 fourth place remaining. Huh? And then you have this is the arrangement. I'm still writing arrangement, okay? Four things, and I'm writing, taking all four things, and I'm writing arrangements. First place B, 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 first place B. Second place A, second place C, second place D. Third place C and D, third place A and D, third place C and A. Fourth place remaining thing, 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 fourth place remaining thing. And then C, 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 second place A and A, second place B and D, second place D and D, third place I can write B and D, third place I can write third place I can write B and D, third place I can write, third place I can write B and D, third place I can write A and D, third place I can write A and B, fourth place, remaining 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 fourth place, remaining. And then D, D. Second place, A and A, second place, B and B, second place, C and C. Third place, B, C, third place, A, C, third place, A, B. Only one thing is remaining, D, A, B, C, D, A, C, B, D, B, A, C, D, B, C, A, D, C, A, B, D, C, B, A. Arranging four things as expected results into 24 ways. Arranging four things as expected results into 24 ways. 4 into 3 into 2 into 1. 24 ways. But you tell me, are not all of them same selections? Are not all of them same selections? I mean, you are selecting the same characters again and again. Arrangement wise, there are 24 different arrangements. Arrangement wise, there are 24 different arrangements, but all represent same selection. All are 24 different arrangements, but all represent the same selection. You are selecting the same four characters, A, B, C, D. That's it. So I say total number of arrangements are 24 or 4 factorial. And then there is number of selections, number of distinct selections. And then there are repetitions happening. My dear friends, number of distinct selections become number of arrangements upon repetitions. I can. Okay, let's keep it like this. And let's repeat the whole process for selecting 3 objects out of 4. And then we will be able to generalize. Just 1-2 minutes and we are done with these counting methods. Just 2 minutes. So now I know that even though these 24 arrangements are representing 24 different arrangements, but all of them represent one selection only. All 24 are representing a single selection because every time you have selected the same thing. Yes, they represent 24 arrangements, but believe me, selection on the front of selection, you have done only one selection. There are 24 repetitions of the same selection. The same selection of characters has been repeated 24 times. Now, let's try to select 3 out of these 4. If we try to select 3 out of these 4, we have ABC. In fact, 2 out of these 4. AB, AC, AD, and BA, BC, BD, and BC, and CA, CB, CD, and DA, DB, DC. You already know this is arranging 4 objects at 2 places. So total arrangements are how many? This is arranging two objects with four objects at two places. So total arrangements as expected, total arrangements are going to become 24 upon 2, that is 12. Total arrangements are going to become 24 upon 2, that is 12. But notice that each selection is repeated twice. There are two arrangements representing the same selection. Notice that there are two arrangements representing the same selection. CA represents same selection as AC. AB represents the same selection as BA. BC represents the same selection as CB. AD represents the same selection as DA. BD represents the same selection as DB. CD represents the same selection as DC. So there are actually only 6 selections you are doing. CD and DC are same selections. AD and DA are same selections. BD and DB are same selections. CA and AC are same selections. AB and BA are same selections. BC and CB are same selections. So there are repeated selections, and each selection is repeated twice. I can very clearly see each selection is repeated twice. So number of distinct selections and then number of repetitions is equal to total number of arrangements. Number of distinct selection was 1 only here. 1 only here, and it was repeated 24 times. That's why you got 24 arrangements. There is only one selection and it's repeated 24 times. Here we have 6 distinct selections, and each distinct selection is repeated 2 times. Each distinct selection is repeated 2 times. We notice a pattern that number of distinct selections are repeated certain number of times, and then we get the total number of arrangements. Then we get the total number of arrangements.
Sir,
The total number of arrangements are always available as number of distinct selections multiplied by how many times each selection is repeated. Number of distinct selections can be written as this 4 factorial upon 4 minus 2 factorial, that was 12 divided by this 2. Also notice that you always have as many factorial repetitions as the number of objects you are selecting. We can generalize that if you are selecting 2 objects from 4 objects, these will be the number of distinct selections, the number of different selections. We generalize selecting R objects out of selecting R objects out of N objects is possible in these many ways: N factorial upon R factorial and N minus R factorial. This is denoted as NCR. C represents for combination, but don't go by the word, these technical words, permutation, combination. Always remember, permutation stands for arrangement, permutation stands for arrangement, and combination stands for selections. So we call it a day.
Sir, once explain that number of distinct selection into two, sir.
Because each selection is repeated now. Let's take one more example so that
Yes,
we
sir.
can understand this. Shashank, Nigam, you have a playlist on this YouTube channel only. There is a playlist now, probability. In that playlist, you have lecture 1, lecture 2, lecture 3, lecture 4, lecture 5, all the lectures arranged sequentially. Let's say there are 5 objects, A, B, C, D, E. Now, 5 objects, I want to arrange only 2. 5, I want to arrange at 2 places. Okay? 5 objects are there, I want to arrange at 2 places. How I arrange? A, and then B, A and then C, A and then D, A and then E. Okay? Then B and A, B and C, B and D, B and E. Then C and A, C and B, C and D, C and D, and C and E. Then D and A, D and B, D and C, and D and E. Then E and A, E and B, E and C, E and D. As expected, we have 4 plus 4 plus 4 plus 4 plus 4, 20 total arrangements. As expected, this is actually 5 into 4. People say that we are going to forcefully introduce 3 into 2 into 1 here. We are going to forcefully introduce 3 into 2 into 1 here. So in denominator also, I have 3 into 2 into 1. Okay. So that way I get 5 factorial in numerator, and in denominator, I get 3 factorial. I'm arranging 5 objects at 2 places. So I would like to write everything in terms of 5 and 2. So I just do one last modification, and that modification is 5 minus 2. Now this is called n factorial upon n minus r factorial. We call it NPR. But suppose you are not arranging 5 objects at 2 places, but suppose you are selecting 2 objects out of 5 objects. Suppose you are selecting 2 objects out of 5 objects. Now, selecting 2 objects from 5 objects becomes selecting 2 objects from 5 objects becomes a different problem. Because selecting 2 objects, you cannot say that I'm going to select C and A, and I'm going to select A and C. They are not 2 different things. Selecting Ahmedabad and Chennai for your next trip is the same thing as selecting Chennai and Ahmedabad. Selecting Delhi and Ahmedabad is the same thing as selecting Ahmedabad and Delhi. So if I was selecting 2 objects out of 5 objects, AC and CA can't be counted twice. Then AB and BA can't be counted twice. Then DA and AD can't be counted twice. Then AE and EA can't be counted twice. Then BC and CB are the same things. Then BD and DB are the same things. Then BE and EB are the same things. then CD and DC are the same things. Then CE and EC are the same things. Then finally, ED and DE are the same things. So we notice that actually each selection is repeated twice. Out of these 5 factorial upon 5 minus 2 factorial arrangements each selection is repeated twice. So do we really have these many selections available? No, only half the selections available. If I have counted 20 arrangements, then selections are 10 only. Because both the white selections are same, both the green selections are same, both the blue selections are same, both the orange selections are same, both the yellow selections are same. So we say number of selections are number of selections become total number of arrangements, total number of arrangements divided by 2. It can be proved that 2 is actually 2 factorial. I mean, if you would have selected 3 things out of 5, then you must have got 6 repetitions of each selection. Each selection would have been repeated 6 times. If you want, you can try yourself. The general thing becomes n factorial upon n minus r factorial into r factorial, which is NCR. We'll continue this journey in the next class. Next class happens on Wednesday.
Today there is mechanics class, sir.
No. Today, now I'll start with the Hindi batch. So today there'll be no class, but yes, you have enough material for further DPP. So you will get a DPP and a quiz on probability. Chalo guys, I'll wind up the session because at 4:30 the class was about to start the next class. So in case you have any doubt or something, you can call me. Drop a missed call, I'll call back and discuss, huh?